calculations. So for the digital filtering, we'll now discuss how exactly we can achieve this goal of limiting the signal bandwidth, because in modern telecommunications and many other stuff, like where you maybe have seen some movies, some scientists analyze, I don't know, astronomy, say, oh, here is the, I don't know, yellow part of spectrum in this time. Yes, so they did some spectral analysis, which we'll also learn to do. But for that, you need to somehow separate the certain frequency components from others. So that means you need certain device capable of limiting the frequency bands. So like this is band 1, this is band 2, band 3. This might be visible light bands, like different colors. This might be different radio channels, Wi-Fi network channels, and so on and so on. But the thing is that we need this kind of a device. Those devices are called filters, yes? And specifically, we'll today discover more digital filters. But before that, let's have a little bit about mathematics, about Z transform. We already know what is Fourier transform. Yes, so that's when we convert our time domain function into some frequency representation of the same function. Now, essentially, Z transform does very similar thing for the digital signals, because for digital signals, as we discovered already before, when you do sampling, that is convert analog into digital signal, your spectrum starts to replicate periodically, repeat over and over and over. So here you have sampling frequency fs, here you have double of that frequency 2fs, here we have triple, and so on and so on. It goes all the way up to infinity. So in a certain sense, you can then kind of take this strip of paper, roll it into a circle, yes, and have this as the repeating pattern. Yes, because once you go over to this point, it starts over again and repeats again by going another circle. So that is actually called Z-plane in a complex plane, yes? And according procedure of mapping the spectrum, which is obtained by Fourier transform into the Z-plane, is called a Z-transform. But there is a little bit more to that, and it's actually a convenient tool of which I will try to convince you that for digital signals, it's actually very convenient to use one. So we already have evaluated samples, like time samples, like x0, x1, x2, like specific points of signal, which we read in time, and also frequency domain and the spectrum samples. When you take those time samples, calculate Fourier transform, display the spectrum, and can conclude something about signal. Now, they are closely related to each other by Fourier transform. Obviously, you get from time domain to frequency domain with Fourier transform, and vice versa with inverse transform. Now, Z transform here is something similar to Fourier transform, except that it maps your time domain not really to the frequency domain, but to some complex Z plane where we have cyclic repetitions. Yes, and main feature of that is that your signal formula becomes a polynomial of certain Z variable, which may be convenient. So let's see some example how is it solved. Let me remind you the idea that any system of any type, that's electronical, acoustical, social, whatever, planet, and so on, can be considered as a system with certain impulse response. So you kind of move it a little bit and it somehow will respond to the stimulus, yes? So you throw some idea in socium and it ignites masses, they start protesting, and etc., etc. Yes, so that's basically like so. So the idea is that each of these systems has its own impulse response, yes, like specific property. And different systems, therefore, are having different impulse responses. That's what making these systems different, because they react to different inputs in different way. Yes, we can actually estimate this impulse response for any kind of system for which you don't even know this impulse response. You have no idea what is the impulse response of this system, but you can send a single simple pulse and the input of it, like influence it with a short and strong stimulus, and then just listen to what happens at the output of the system, like a bell, which you hit once and then you listen how it rings, longer or not so long, with different tone, and so on and so on. So that's how you define the impulse response. It's a reaction to the single uh, hit, in essence. Yes, so the single pulse. Okay, now if we speak about more complex situations when you have this impulse response denoted by H, then you have any possible arbitrary signal xn, like not necessarily a single pulse, but any kind of a signal. You do know input signal, you do know how the system reacts to the pulse, but you don't know what is going to be predicted output of the signal. Like that's what you want to know. In that case, the output of this signal is depending both on this, what you have specified in the input, and on the, how we can also say, the inner state of this system itself, yes, its impulse response. So the formula is called a convolution because it's quite complicated, convoluted formula, yes, and you can see that there is some time shift, so input by impulse response time shift, summation, blah, 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 blah. Well, not so easy to calculate. Well, of course, in MATLAB we have a function, conv, yes, which you can use, and it's actually how filter also works. So you, for filter, also have impulse response, also have output signal, and it's just that for filters you usually design the impulse response in a very specific way so that your filter does that, that, or that. So you can think of it as a system which you tune to do specific tasks, specifically filter specific frequencies, yes? And there are methods that allow you to calculate predictably what you are going to get. So let's try to calculate some output signal for this system example here, that you have impulse response of 1, 0.5, minus 0.5. So that means whenever you send the symbol 1 at the input, it's going to go at the output immediately. After the symbol ended, it's going to produce half of that value, and after that symbol, another half with a negative sign. So basically you send 1, 0, 0 at the input, and at the output you are going to get 1, 0.5, and minus 0.5 as a reaction to this single pulse, yes? So that's what is this impulse response. But in our situation right now, we want